Okay, so we are talking about value. Today we will start the eigenvector. So just to recap, so we have a square matrix. A is a square matrix, n by n matrix, and we are taking the characteristics polynomial of this matrix, which is defined as determinant of A minus, this is also n by n matrix. So this is a characteristics polynomial, and if we take the equation, if we equate to 0, then this will give us a characteristics equations, and the roots of these equations are the eigenvalues. So this is a n degree polynomial. So it has n roots. Roots of this equation are eigenvalues. So if lambda is an eigenvalue, that means, so this is the equation. If lambda is a root, then x minus lambda is a factor of this polynomial. Now, if the lambda is a root of r times root, that means root of multiplicity r, then we must write this as x minus lambda to the power r and some other polynomial, where phi lambda is not equal to 0. Then it could be another multiple. Then lambda is a root with multiplicity r, and this is called algebraic multiplicity. So lambda is coming r times. It has n roots, among them r roots are lambda, repetition roots. Okay, so this is called algebraic multiplicity of a eigenvalue. So then if this is happened, then r is called algebraic multiplicity of lambda. Later on we will define the geometric multiplicity, which is based on the eigenvector. Okay, so this is the thing, and we also have seen that this lambda may not be from the same field. So this we have a matrix A, which is a square matrix, where Aij is coming from the field, which is a field under this operation. Now, Aij, it could be real number or anything. So it is coming from the field. So in the last class we have seen, if you take the matrix like this over a real 0 minus 1 1 0, then the corresponding characteristics equation is x square plus 1, characteristics equation is this. So x is plus minus I is root over of minus 1. So this is a complex number, but our field is a real field. So here field is real field. So eigenvalues are not from this field here. So this is one example. And in the last class we have also seen that if the if we have a non singular matrix, then there has to be a if we have a singular matrix, if the determinant of this matrix is 0, then there has to be eigenvalue with 0. 0 is the eigenvalue, is an eigenvalue of A. This is because we have seen from the characteristics equation, this product of the eigenvalue. So the characteristics, this we discussed in the last class. Just to recap, characteristics polynomial can be written as C0 x to the power n plus C1 x to the power n minus 1. This is an n degree polynomial. Then Cn, okay, where Cr is the minus 1 to the power n minus r, and the sum of the all principal minor of order R. Sum of all principal minors of order R. So, that means, if we put Cn, Cn is nothing but determinant of A, because principal minor of order n is the determinant. And we know that this is a polynomial of degree n. So, we know the product of the eigenvalues, if there are n eigenvalues lambda 1, lambda 2, lambda n, then the product of the eigenvalue will be written as this coefficient C n by C 0. Now, if the determinant is 0, then this is 0. So, product of the eigenvalues are 0. So, that means one of the eigenvalue must be 0. And on the other hand, if we have a non-singular matrix, if this is not 0, then there should not be a 0 eigenvalues. So, this is the result we have seen. Okay, now we will talk about something more on the eigenvalues. Suppose we have a non-singular matrix A, and if lambda is an eigenvalue, then the 1 by lambda is eigenvalue of A inverse. So, let A be non-singular. So, that means it has a inverse. This implies determinant of A is not equal to 0. That means A has inverse. A inverse exists. Okay. So, non-singular means there is no 0 eigenvalues. So, let lambda, which is not 0, because 0 cannot be eigenvalue of this. Let lambda be an eigenvalue of A. Then this theorem is telling, this is a theorem, then we have to show 1 by lambda, which is exist because lambda is not 0. 1 by lambda is a eigenvalue of A inverse, is an eigenvalue of A inverse. Okay, this is a theorem, you can say. So, how to prove this theorem? So, to prove this theorem, we need to take A is an eigenvalue. So, that means lambda is an eigenvalue of A, that means determinant of A minus lambda I n, this is 0. So, lambda is a root of the characteristics equations. Now, we need to check whether lambda inverse is also an eigenvalue of this. So, for that, so we will use this. So, proof we are doing. So, det of A minus lambda I n is equal to 0. Now, we take the det of determinant of A inverse minus lambda inverse I n. If we can show this is 0, then lambda is inverse is an eigenvalue of this. So, this we have to show to be 0. So, what is this? This is nothing but det of A inverse we keep, and here we write lambda inverse is there. Now, A inverse A, which is basically the identity. So, now this we will write as det of A inverse minus A inverse, lambda is a constant, lambda inverse is a constant, we can write this as this. Okay, now, we take A inverse common from this, I minus lambda inverse A. So, this is nothing but det of A inverse, det of identity matrix I minus lambda inverse A. So, this is nothing but det of A, then the inverse, and we can take this lambda common n times. So, this is lambda inverse. So, this is lambda inverse n, and determinant of lambda in minus a. Now, again we can take minus common over here. So, this will give us det of a, which is none of this is 0. So, this is we can take minus, and this is det of a minus lambda in. So, this value is 0, because lambda is the eigen value of this. So, this whole thing is 0. So, that means det of A inverse. So, this is the characteristics equation of the A inverse. So, it has a root lambda inverse. So, lambda, this implies lambda inverse, this implies lambda is inverse is an eigen value of A inverse. So, this is the proof. Okay, lambda is the inverse is the eigen value of A inverse. Okay, now we will see another result, another theorem. So, if we have a matrix A, and if we have a square matrix, sorry, non-single, all are square matrix. So, this is another theorem. So, we have a square matrix A, which is could be singular or non-singular. We have no, we do not know anything about A, whether it is singular or non-singular. But and this is one matrix, and we have a matrix P, which is non-singular matrix, Then this theorem is telling that P inverse A P and A has same eigenvalue. A and P inverse A P have the same eigenvalues. Have the same eigenvalues. So, that, so how we can show that two matrices are having same eigenvalue? If their characteristics polynomial are same. So, that we are going to achieve. So, this we refer as some matrix, this is we got B matrix. So, we have to show that characteristics polynomial of A is same as characteristics polynomial of B. So, what is the characteristics polynomial of B? Characteristics polynomial of B is basically determinant of B minus lambda x I n. So, let us write B. B is P inverse A P minus x I n. Okay, so, this x I n we can write as P inverse form. So, P inverse x I n into P, because P into P inverse will give the identity. So, this we can write as determinant of, we can take P inverse common over here, A minus x I n into P. So, product is the determinant of A into B is same as determinant of A into determinant of B. So, if we apply that, it will give us determinant of P inverse into det of this into det of P. So, this and this will give us 1, and this is nothing but det of A minus x I n, which is the characteristics polynomial of A. So, characteristics polynomial of these and these are same. So, that means it has these two has the same eigenvalues. So, this is the proof. These two has the same eigenvalue. So, this is the proof of this theorem. So, if we have a square matrix, then we will be getting basically the same eigenvalue of this. Okay. So, now we will define eigenvector of a matrix. So, we defined eigenvector of a square matrix. Okay, suppose let A is a square matrix, n by n matrix. We define the eigenvector. Eigenvector is a, so this square matrix over a, so this matrix is coming from, elements are coming from the field. So A I j is coming from the field under the operations plus, and we have two operations in the field. Okay, so this matrix is over field. This field could be the real field, complex field, set of real number, set of complex number, but in general this is a field. Okay. Now, a non-zero vector x, which is a non-zero vector, x is coming from f to the power n. So, f to the power n nothing but f cross n time. So, this is a n tuple. X can be written as x 1, x 2, x n. I mean, the transpose of this is a n tuple. So, it is coming from a, so x transpose is this, we can say, or yeah, this is x and x transpose say is a field. Anyway, so this is coming from the, this is a tuple, either you write in row way or column way. This is a n tuple and elements are coming from the field, all of these x's are from the field, and x is non-zero. Non-zero vector, a non-zero vector x is called a eigenvector called an eigenvector vector of A if there exists a lambda scalar, lambda again from the field, such that A x equal to lambda x, such that A x equal to lambda. This is the definition of, this is the definition of eigenvector. This is the definition. So, what is the definition? That if x is a non-zero vector x is called a eigenvector of a matrix A, if and only if there is a scalar of the same field, there is a scalar such that A x equal to lambda x, it is satisfying this equation A x equal to lambda x, then x is called a eigenvector of the matrix. Okay. And lambda is the corresponding eigenvalue. So, we will come to that. So, what do you mean by A x equal to lambda x? So, once we have A x equal to lambda x, that means A of lambda I x equal to 0, we got these equations. Now, we are looking for a, this equation we are familiar with. So, this is nothing but the characteristics equations. So, this is a homogeneous equation, homogeneous equations, and so this is a, so the how we get the eigenvalues? Eigenvalues we are getting by the roots of these equations. So, that means this x is the non-zero solutions of this homogeneous equations are called eigenvector, and this lambda is the corresponding eigenvalue. So, for each eigenvector there is a for each eigenvector there is eigenvalues, but the question is the one eigenvector can corresponding two eigenvalues. So, that we have to check. So, this will give us the eigenvalues, and the eigenvalues will give us. So, let us check that. So, if we have a eigenvector, so an eigenvector vector gives us a corresponding to a eigenvalue. Now, that means if x is eigenvector, that means there is a lambda such that this. Now, the question is this unique, this lambda? The question is, if we can we get two eigen value corresponding to a eigenvector? Answer is no. Why? So, this eigenvector will correspond to the unique eigenvalue. So, that means corresponding to a eigenvector, we cannot have two eigenvalue lambda 1 lambda 2, where they are not same. This is not possible. Why? How to justify that? Okay, suppose it is possible. Suppose for a given eigenvector, we have two eigenvalues. One is lambda 1 and another one is lambda 2. That means what? That means we have two equations, A x equal to lambda 1 x and A x equal to lambda 2 x. So, from here what we can do? We can just and where lambda 1 lambda 2 are coming from the field, where the matrix element are there. Now, what we do here? Now, we can just subtract these two and we get lambda 1 minus lambda 2 x equal to 0 vector. So, now this is not possible because x is non-zero, x is a non-zero vector and also this is a non-zero scalar, because we. So, to happen this we need to have lambda 1 equal to lambda 2. So, that is the uniqueness. So, for a given eigenvector we have a unique eigenvalue. So, one eigenvector cannot corresponding to two different eigenvalues. So, in other words, the eigenvector is giving the unique eigenvalues. Okay. So, this is one observation, but other way, suppose we have given a eigenvalue, then how many eigenvectors are there? Let lambda be an eigenvalue of a matrix A, which is n by n matrix. Then it will lead us to a some eigen vectors. So, at least one eigenvector. So, that means this determine this characteristic. So, lambda is the root of this characteristics equation. So, this is a characteristics equation. So, lambda is the root of this characteristics equation. So, that means determinant of A minus lambda n is equal to 0. So, that means if we consider this homogeneous equation, so A minus lambda I n equal to S, if we consider this homogeneous system of equation, then it has, because this determinant is 0, if determinant is non-zero, then it has only one root which is 0, or only one solution which is 0, but determinant is equal to 0. So, that means it has many solutions, non-zero solutions, infinite number of solutions, and each of these is a eigenvector. Each of these non-zero solution is corresponding to the eigenvector corresponding to this eigenvalue lambda. So, each x not equal to 0 solution of this is called eigenvectors corresponding to the eigenvalue lambda. Okay. This will corresponding to the eigenvalue lambda. So, and if x is eigenvalue of if x is eigenvector, suppose x is eigenvector. So, that means sorry. So, if x is eigenvector, so a minus lambda I n x is 0, then alpha x also is eigenvector, because x minus lambda I n alpha x, alpha is a scalar. This is also an eigenvector, x is non-zero. So, we have infinitely many eigenvectors corresponding to a eigenvalue. And if we consider this set, so we have infinitely eigenvector corresponding to a corresponding to an eigenvalue lambda. So, given a eigenvalue, we have infinitely many eigenvector, because that those are the non-zero solution of this system of homogeneous equations. Okay. So, we will continue this in the next class. Thank you.